Hey, and welcome to the Nordic Tech webinar, Cloud Connectivity and Protocols for the Internet of Things. I'm your host, Marcus, and this is my colleague, Karl Richard, who will join us later in the webinar. Our agenda for today is to look at the protocols that are involved when a device talks to the internet. So we look at the application layer, what's to consider there, down to the transport protocols, because there are a lot of decisions to be made that influence the amount of data a device is sending. And saving data is very, very important because it is a cost factor, but it also influences power consumption. And this is where Karl Richard will then also talk later about this aspect of when developing a cellular IoT device. Power consumption is equally important and will make or break a great product. So let's dive into it. First, let's look at a typical setup for an IoT device, and this is how what you see in the wild, but this is also how, for instance, the Thingy 91 is connected to our IoT platform, NRF Cloud. It's using MQTT for device messages like sensor readings, the GPS location, the flip data, and it uses the digital twin to store information about the device and also configuration. On the other hand, if there's a firmware update, we will download the firmware itself over HTTP because HTTP is a protocol that's suited better. There we already have a decision to built in where we made a separation on the protocols, and we'll see in the course of the webinar how that came to happen. The four kinds of data we need to actually consider, and I already mentioned them, are one, the device state, second, configuration, third is historical data or past data, and fourth, firmware updates. They have distinct characteristics and it makes sense to look at them individually. First, device state. A device needs to send its sensor readings like position and temperature and information about its health to the cloud. One of the important health information is battery level. The reason why we also store this in a digital twin is to enable the cloud backend, an application to query this data immediately and not depend on the device being able to respond to a query right away. Because devices will be offline in many scenarios, or probably most of the time. State is the information about the device, and you could say that the device owns this information. It is the authority and provides updates to the cloud about its state. And it's really important to only send updates if the device actually needs to send it, if there's relevant information in the data. So for instance, was there motion detected? So we know something has changed and it makes sense to start a GPS and acquire position, or did enough time pass? So we want to send a battery level every hour or every day to the cloud so we can monitor for critical level there. And third, sometimes you want to decide, is my connection good enough? Do I have a strong enough signal where actually the likelihood that this message will get out is high enough? The second one is device configuration. This is the opposite part where the cloud tells the device to go into a certain state. You could think about this as actually the configuration and the behavior of the device can be influenced. Especially this is important during development to look into this because sending a firmware update with an update in the behavior is very expensive. It's like 2 to 3 times magnitudes larger than a single control message. So build in some form of configurability into your firmware, which allows you to tweak behavior during development, especially if your devices are not on your desk but out in the wild. And if you're developing a product that interfaces with the physical world, you need often a state. For instance, if you're developing a smart lock that can be unlocked through the internet, you need to send the state of the lock, open or closed, to the device based on user interactivity. Again, here we use the digital twin because this allows the backend to write directly to the digital twin, and then the IoT broker will take care of eventually transmitting the desired state to the device. We don't need to wait for the device to be online. This will be handled by the digital twin. It's important to also look at historical data because for now we only talked about configuration and device state, which are both immediate, like they are now. But let's have a look at a coverage map from Telenor. This is a coverage map for part of Norway. It doesn't really matter. The important part here is we can see there are really areas where we have strong and good reception, and then there are areas where we have no reception. If you look closely, these are on the ridges of mountains. So if we had a herd of reindeers in this area and we gave them trackers or sheeps, and they would send updates only in real time when they have connectivity, we would see our sheeps are most likely very happy on the ridges. But we would see, oh, they are never here down, maybe not in the water, but on the water. This is obviously false information. So we need to build devices that are able to cache positioning information. You will get GPS connectivity and positions down in the valley because the satellite is pointing down to the Earth. And if the sheep then at some point walks up a ridge and gets LT connectivity, which is traveling more or less horizontally, then it will not only send the current position, but also the past positions it had here. So past data is really important and behaves a little bit differently than state. And it's important to consider. And the last part I mentioned earlier, however, is firmware updates. The reason why this is separate is, again, it's way larger than a typical control message. A typical hex file is around 250 kilobytes of data, which we need to transmit to the device. It really makes sense to transmit this over HTTP because HTTP supports resume. So a device can start downloading a firmware update. If it loses connection, it could come online later and resume from a byte range it doesn't have. It doesn't need to start over again. This is a feature which is not implemented in MQTT. So that's why it's also something you need to really consider when looking at what is it my device is sending and receiving in data. It's really, I can't stress it enough, but there is a great potential for optimization in picking the right protocol because the out-of-the-box choices are kind of very generic and more optimized for developer experience. And we will look at this in a moment. And there's a lot of potential for saving data. And because this will be multiplied thousands of times when you have devices in the field, this will translate directly to cache savings. So let's look at the data protocols we typically use in IoT solutions today. This is JSON and how we can maybe replace it. JSON, to sum up, is here's an example of a geolocation message encoded in JSON. It's latitude and longitude. This is the accuracy, like how precise was the GPS location in meters around the center. This is the altitude above sea level, the speed in meter per seconds, and the heading, in which direction the device is pointing. This is 0 because the device was not moving at all. And because I already talked about historical data, it also contains a timestamp. We need to timestamp data on the device and not on the cloud side. So if this message arrives later, the cloud doesn't think, oh, this just is the current position. We need to know when the device was at this position. So JSON is the default data protocol for IoT and e-commerce cloud vendors like Amazon, Microsoft, and Google. This is their default out-of-the-box device because it has big advantages. It is human readable and schemaless. There is schemaless meaning the data itself is self-describing, so it tells you what's contained in the message. This makes it a great choice during development. It's easy to look at the data, and it's great for humans, but it's a big overhead for machines. Machines don't need this context information. So that's where one of the possible optimizations for the data protocol comes in. We can look at the data protocol that removes all of this schema information. We can, because the device in probably all cases will be sending the same message over and over and over again. Your device will be sending GPS updates, and GPS updates only probably. It won't just suddenly start sending information about a smart lock, because that requires a firmware update. So it makes sense to take out the schema information and only transmit the actual contents of the message. Just the these are six floats and one large integer. This is actually the payload that is relevant. And protocol buffer takes this approach. You define a schema on both sides and get a byte stream that then can be parsed. So this is kind of the most optimal protocol, and it's more robust than just sending pure binary data. So pure binary data would be even better, but that creates much more issues with dealing and handling with it than using something that gives you a little bit of structure. So protocol buffers allows you to save, for this specific message, 42%. This is obviously depends on the JSON message you're sending, how big the object is, but it's big. It's a lot of savings, and again, you have to think about multiplying this many times per day and per device. So this translates directly to money you're not spending on data usage. However, protocol buffers is not available there's no official C implementation, but there is flat buffers. It's also an official Google project. They have a C implementation. They have a great addition, is especially optimized for resource-constrained devices. It allows you to access the data in the message without needing to parse it. So you have one big chunk of memory, and you can directly address the values in there. So that's why there's a little bit more overhead, because they provide these pointers, not C pointers, but kind of pointers to the message, which allows the direct access. Unfortunately, there is no official support in Zephyr and NCS. So if you don't want to go into this direction right away, there's kind of an intermediate step, which is called CBOR. Compact byte object representation is a direct mapping of JSON values to a binary structure. There's no need to configure schemas on the receiver and the sender side, and it's supported in Zephyr. Zephyr uses the tiny CBOR implementation by Intel. And here again, looking at the message, at the GPS message, in CBOR we can save for the same message around 24%, which is again significant. This is 1/4 of every message that the device would be sending. So it absolutely is worth looking into using this kind of encoding as a first optimization step. To sum up, look into denser data protocols. JSON was made for humans. We are dealing with machines. It's nice and easy to have it during development, to have JSON everywhere, but it is a big overhead, which kind of there's no good reason to have it in your production device. It's not only a cost savings, but the less data you send, the less energy your device consumes because it's spending less time sending data, and the less bytes you send, the lower the risk of actually a failed transmit. Because if your device is moving around, it could happen that it loses connection, then it has to start over again. So yeah, there are multiple advantages of sending as few data bytes as possible. Now we're going a little bit further down on the layers to the transport protocols. It's a little bit of the same story. We look at the default protocol that's offered by the cloud vendors, MQTT and TLS, and then look at some of the alternatives, which are not so common, but are worth looking into. First, MQTT and TLS. This is out-of-the-box support from Amazon, Azure, Microsoft, and Google. It's a protocol that's a great fit for Internet of Things in general. It's event-driven. It is a pub-sub model, so once the connection is established, both parties can send messages back and forth, and you can kind of you can decide based on the topic which messages you're interested or not. So it's super flexible, and it in general matches good IoT, but it's problematic for a resource-constrained device like the NRF9160 and a cellular connected device in addition, because there is a big overhead. From MQTT itself uses topic names to basically address where a message should be going, and this is contained in every MQTT package. And this is 50 to 60 bytes per message you're sending out, and this can obviously over time it accumulates, and this can easily make a typical message maybe has 200 to 500 bytes. So this is in the 5 to 10% range of a total message size. So it absolutely makes sense to kind of look into optimizations there. And then the TLS handshake itself. If you're using TCP and TLS, the handshake, the first connection is around 10 kilobytes. After that, after you've connected, then it gets lower, and you probably don't need to do a handshake for every message. You will be doing most likely one handshake per day or per hour, but 10 kilobytes is significant. However, these are the default protocols, so obviously we support it right out of the box in NRF Connect SDK. If one optimization there is using the same technology, roughly MQTT, and there is an sensor network SN specification which is optimized for IoT specifically, where the overhead of using strings for topic names is reduced. So after connecting, a device basically has a map of topic it's subscribed to, and for every message it only needs to send this number. So it's using 1 byte per topic instead of 50 or 60 bytes. And this protocol also allows the use of UDP. MQTT itself does not support UDP, but MQTT SN supports it. So we can leave this realm of the TCP and TLS connection and still use encrypted and get delivery guarantees using DTLS, but in a network that doesn't need such a big overhead in TLS handshakes. Unfortunately, not supported in NRF Connect SDK, and it's not supported by cloud vendors. However, you can build this support yourself by building a gateway in front of AWS or your cloud provider, and that can be a pretty stateless gateway, which doesn't need to know too much about the devices. It just will forward messages. However, yeah, it adds an extra layer of effort for you. One thing that we see really becoming more and more popular is CoAP and LWM2M. CoAP is and both protocols have been developed specifically for IoT and resource-constrained devices, and they have already used in telco clouds for the device management. So for telco providers to push firmware updates to devices, they use this kind of protocol, and they also employ it in their own cloud offerings. So Verizon's ThinkSpace and AT&T's IoT platform, they offer you to use CoAP and LWM directly. They provide a thinner and protocols, and also allowed to use UDP, but they also offer workflows on top of it. LWM2M specifically in the upcoming 1.1 version offers predefined workflows, for instance, for FODA, firmware updates. So you can build, using this standard, you can build roughly plug and play devices where the underlying implementation doesn't really matter, and the protocol already offers you everything you need to operate a product without you needing to come up with your own JSON or MQTT topic protocol. It's very nice and very much worth looking into. However, there's, again, unfortunately, no support for on the big e-commerce providers. But again, you can solve this by building a gateway. And I did a proof of concept. You can find it here for taking Leshan, which is an open source project from the Eclipse Foundation, which offers is probably the most capable LWM2M 1.0 implementation, and put it in front of an AWS gateway. So it just demonstrates that it's possible. It's not production ready, but it gives you an idea of how to solve this, how to build your gateways between your optimized protocol and the powerful IoT broker that's offered by one of the e-commerce cloud vendors. Because this is a scenario which I think we will keep seeing and continuing. I know that some of the e-commerce providers are working on adding more support. And if you look, for instance, to Alibaba, they offer CoAP support. So it's also worth looking at actually the cloud provider side if they may be offering you something. And as I said here, there are already platforms, especially for IoT, which are designed for these resource-constrained devices in mind. Now, yeah, we talked a lot about the data that's the device sending and to reduce it, but actually, how do we measure it? And the measuring needs to start, I can't stress this enough, needs to start very early, basically from day one, where you start building your product, start measuring data. Because only over time, having devices in the wild, in real usage, you will really understand how much data are you sending, how often, and this will be an important input once you start negotiating with your connectivity partner. And unfortunately, it's very tricky to measure data at the endpoint where it's terminating, so at your MQTT broker, especially if you're not controlling it. So in AWS IoT, for example, you get JSON messages at the end. So you could count how many messages, how big they are to understand how much data the device is sending, but you don't get the lower level transport layer statistics. And you won't get information about maybe a device is trying to send a message 3-4 times until it actually is delivered because the connectivity is spotty. So it really makes sense to measure data consumption on the device itself. And the good thing is that the 9160 modem provides connectivity statistics for this. You can turn them on using an AT command. 80% xconstat equals 1. This would turn on this will tell the modem to start accumulating device connectivity statistics, and using 80% xconstat question mark, you can read out these statistics. Here's a very simple It's just a few lines of code that you need. You can find an example where I edited to a real application under this link. And what it gives you, if you read out this data, it gives you 6 numbers separated by comma, 6 integers that get bigger over time. So it's just accumulated every time you ask it. So it will give you, since you started monitoring, how much happened. And these numbers are numbers of SMS, not so relevant these days. What's really relevant is the number of kilobytes transmitted and received. And the idea here is that you will include this, for instance, in a message that you send once an hour or once a day. Like not too often to not kind of influence your regular data profile, but transmit it along when you send, for instance, the battery update. So you get a feeling and can collect this on the cloud side and create a report on how much data your device is actually using. And the good thing is that this includes everything. This is the low-level byte counter on the modem. So that includes FODA, that includes all MQTT messages. So that's probably the best way to actually measure the data consumption. Now, our devices, at some point, we are going have to look at the physical layer. Data is one important aspect, but the wireless radio protocol we are picking also has a big influence on the product we are building. And there will be another webinar especially about this, so we'll make this really short, but just to give you an overview. We have these 2 protocols supported in the NRF 9160. One is LTE-M and the other one is NB-IoT. In this picture, you can roughly see LTE-M is for stuff that moves and is kind of interactive, and NB-IoT is mostly for metering solutions, industrial applications. Why is that? LTE-M is using the same technology roughly as our smartphones are using, however, with a much reduced bandwidth. 375 kilobit per second downlink, 300 uplink, which in the end make around 100 kilobit per second actually usable throughput for an IP stack. It's okay, yeah? So a firmware update using LTE-M, the 250K, will take maybe 20 seconds roughly. So it's reasonably fast even for bigger payloads. It has great latency in millisecond range because it uses frequencies above 2 gigahertz. It supports also roaming, which is very important for devices that move around. However, these higher frequency bands don't penetrate very well through walls and into the ground. That's why it's not so commonly used in metering applications, which you typically have inside buildings or in cellars. NB-IoT kind of addresses this. It uses typically frequency bands below 2 gigahertz. That means better ground penetration. However, that also means a lower bandwidth. So there's not so much data you can send over the wire, and it has no roaming support in the standard. However, some telco providers will offer you a custom solution for roaming in NB-IoT networks. The comparison looks like this. Again, a little bit from the picture before. LTE-M, use it for applications that need to move around a lot, which need a high interactivity. NB-IoT is great if you're building a metering solution or something that is fixed in place. If it's a smart building or metering, then it makes sense to use NB-IoT. Now, my colleague will take over and talk about the energy consumption and what he found out when looking into this.
Hello! I'll now talk a bit about energy consumption considerations that should be made when working with application protocols on a cellular device like the NRF 9160. I wrote my master thesis on this subject, which I handed in last spring before starting to work here at Nordic Semiconductor. In my master thesis, I compared TCP and UDP represented by MQTT and CoAP respectively. I tested both protocols over NB-IoT and LTM using the NRF9160 and used the data that I gathered to empirically model the power consumption of the device with relation to payload size and transmission interval. I'll not talk that much about the modeling now, but more about the results I got and the observations I made during the research. First, a quick run-through of the experiment setup. I used the NRF9160DK version 0.85, along with the NRF Connect SDK version 1.2. For current measurement, I used the OTI ARC, and I used the Norwegian network provider Telenor with their LTM and NB-IoT network. If you want to learn more about power measurement on the NRF9160 SIP, this will be more thoroughly covered in our webinar the 9th of December. For the firmware, I wrote two applications, one using MQTT and one using co-op. Both were configured to use the power saving mode of LTM and NB-IoT, along with regular transmissions to most realistically emulate a real sensor operation. I also had increasing payload on the transmission so that I could do measurements on the power consumption with relation to payload size. The applications achieved an average sleep current of 200 microamperes, which is not that good, but I'm decided to focus more on comparing the actual protocols and their performance with relation to power consumptions instead of optimizing my own application. On that note, let's talk a bit about factors that contribute to the energy consumption of the device, especially with relation to the application protocols and the cellular network. Common denominator for both of them is the establishment of a connection. And on application protocols, this is especially relevant for TCP, as it requires more back and forth to establish the persistent connections, and more data is required also to maintain this connection. Furthermore, to ensure reliable communication, acknowledgements are used, and these results in unpredictable behavior, as it can take time before an acknowledgement is finished, and you will also need to stay awake for all of this time. This is applicable to both co-op and MQTT. Furthermore, payload size, of course, contributes to power consumption, but we will see that it's different for LTM and NB-IoT when I show you my results later. And then finally, it's important to think about protocol-defined limits. When you work on a network today, there are so many protocols that work together, and many of them have limits defined by the standard. One of them is namely maximum transmission unit, which can affect how much data you actually are allowed to send, or how you have to split it up. And there's also maximum segment size, which is a TCP imposed limit, where the protocol began segmenting the data into different parts. On the cellular network, again, connection is important. When a device connects and registers to the network, it consumes quite a lot of power. But if you use the power saving mode, you can avoid the re-registration when you reconnect to the network. When using PSM, you will also have the RRC inactive timer, which is how long the device will stay active after a transmission has occurred. This, as you will see later, can impose a very big power consumption on the device, and it's also decided by the network, so you have no control over it yourself. There's also several other parameters that affect how the device behaves within this RRC inactive time, but you can look at those in our online power profiler. And of course, reception quality also has a part to play, but I have not looked at this in my research. Here is a timing diagram that depicts the different power levels that can be expected when doing a transmission when the device is in power saving mode. We can see initiation of connection, as well as TXRX before the device stays connected to the network, and for the RRC inactive time countdown. Then it will then enter into PSM if not configured for active time afterwards. We can see some real life examples here. This is measurements done for MQTT over both NB-IoT and LTM. We see the device entering connection here, doing its transmissions, and then staying active for the RRC inactive countdown. We see the same here for LTM. You can also see there's very big differences between NB-IoT and LTM, at least in this network configuration, where LTM listens to the network more often during the RRC inactive countdown. And we will see that even though the LTM transmission takes shorter time, it will consume much more power, also due to the higher peak currents. Which takes us on to some of the results. First, I want to show you these plots depicting energy consumed during transmission in relation to payload size transmitted. The data is plotted with the RRC and active energy both included and excluded. The reason for this is to show you how significant this is in the total power consumption during a transmission. You can see it especially here for LTM, but it's also very apparent for NB-IoT. And the sad part is that this is a network parameter, so we cannot affect it ourselves. So I recommend that you grow familiar with your network and the parameters they provide, so that you can figure out the expected power consumption for transmission on your device. Next up, I want you to notice here that NB-IoT has a quite linear dependency with payload size, so the more data you send, the more energy you can expect to use. While LTM, being a higher capacity protocol, is not affected that much by the power payload size. Though we can see here, especially in the TCP operation, that there are some very large spikes in the power consumption, and I believe this is related to the RRC and active timer being restarted due to TCP operations on the network. Notice here as well that there is a quite significant increase in power consumption for the MQTT measurements, both here in the NB-IoT and in LTM measurements. I believe the reason for this is the maximum segment size of the TCP protocol, which is standardized at about 536 bytes. And you can see that this increase starts after that point. So, and the point by presenting that is that you need to be familiar with the application protocol you're using and the limits imposed on that, because transmitting one more byte can suddenly increase your power consumption by a lot, and it's important to be aware of that so that you can avoid these kind of power surges. Next up, I have some plots on the variation within the message energy measurements. You can here see that the energy consumed on NB-IoT operation is quite consistent both for co-op and MQTT, while over LTM, surprisingly, we have some quite significant power variation for MQTT and also more variation in co-op. The reason for this is, as explained, that we have some outliers from TCP operations that restarts the active timer. Here are some plots depicting the transmission time of messages with different payload size. Here again, I've added the RRC in active time just to see how long the time the device actually was active. And you can see here that opposite to the energy, the transmission time is not as dependent on payload size. But we can still see how the MSSS affects how long time the device stays active when larger segments are sent. When it comes to the variation in the transmission times, we see, as expected, that NB-IoT has is much more prone to latency and variation in latency, while LTM, especially using co-op, has a very, very narrow variation. So you can expect fast and predictable timing when using co-op over LTM. We see that it's also smaller for MQTT on LTM compared to NB-IoT, but again, as I mentioned earlier, we have some outliers here. And now for some final observations. I will use this slide to summarize some of my observations, as well as giving some general guidelines on what could be good configurations for different IoT applications. First and foremost, TCP is not ideal for low power operation. We saw this with general higher power consumptions for the MQTT measurements, but still MQTT is a very popular and well supported protocol. And you could, if your device is not that power constrained, it's a very good choice. However, for power constrained devices, I would say co-op is the better choice, as it has less overhead compared to MQTT while still maintaining reliable transport. Though it's not that popular, and I hope that will change in the future. When it comes to the cellular standards, We have seen the classic result here that LTM boasts high speed and high capacity, while MBIT is slow and have low capacity. We have also seen that MBIT is the energy consumption of MBIT is linearly dependent with payload size, while for LTM the power consumption is not correlated with payload size. And if your network provider gives you a short RRC inactive countdown, that means that LTM could be the better choice if you transmit large amounts of data. So have that in mind when designing your application, and be well aware of the parameters provided by your network provider. However, make sure that you are aware of the more spurious energy consumption in LTM, especially when using TCP. And for some final words from me, generally for sensor applications, you should transfer large amounts of data rarely, rather than small amounts often, as this will result in less power draw overall. And lastly, know your protocols and know their limits. Thanks.
Hey, it's me again, Marcus, with the summary. Well, I guess the one summary is start testing as early as possible. We'll look into all the different aspects that we mentioned before. What data are you sending? How do you package this data? Which protocols are you using to send it? Because there's unfortunately no silver bullet. There's not one right solution for all the different scenarios you can build a product on using the NRF 9160. That is the challenge, but also that makes it so interesting to start prototyping on this. For all scenarios, however, really being conservative on data is key, because these costs are huge relatively compared to what we use to smartphones, and ultra low power as well is an important factor to look into, because there's no real good scenario for wasting energy. Even if you think, oh, I'm building a metering solution which goes into a cellar where I maybe have mains power, but then again think, do you really want somebody to lay a cable to this device so you have mains powers? Or maybe build a device with a decent battery that maybe can last 1 or 2 years, so you can save the installation effort and somebody just slaps the sensor somewhere and forgets about it. So I mentioned before prototyping. We can't stress this enough. And at Nordic, we really try to encourage you and make it as easy as possible to get to your first working proof of concept quickly. And there are two tools that I'd like to introduce to you quickly. One is NRF Connect for Cloud, which is a cloud backend where we host the resources. You buy one of our DKs, they come pre-provisioned with a certificate that connect directly to it, but you can also create your own certificates to connect to this cloud endpoint and can totally focus on designing the hardware and getting kind of your feet wet in the hardware design phase. However, if you want a little bit more flexibility, and even you want to run it in your own cloud, and we have Bifrost. This is a project I started a year ago and is now is incubated into an official Nordic product. So this is happening in the next month. But however, already today we provide a really concrete end-to-end example of an asset tracker, a CAT tracker, on AWS, including a firmware that's from the ground up optimized for ultra low power and using smart decisions on the device to decide when to send data. That's it from our side for today. Thank you very much for listening and happy connecting your devices. Please share your feedback. Here again, our email addresses. I'm on Twitter at CoderByHeart. If you liked what you saw, then please mention the hashtag. And if you have questions which are maybe beyond or related, I always invite you to go to our fantastic support platform, DevZone, and we will have people answering your questions every day there. And finally, there is more webinars coming up. So please also go to nordicsemi.com/webinars and sign up for the next ones, and always have a look out for what we put up for you there. See you soon. Bye.